So, good evening everyone. So, so we will start with today's session. You can watch the video later to cover up the things. So, we will start the session here. Yeah. So, okay. So, welcome back everyone for the session on exploring nonlinear dynamics from basics to applications on the session 7. So, in this session, we will look into the application of this linear stability analysis and the bifurcation theory. So we will see some MATLAB tutorials and we will work on the details. So we were left out with some methods which needs to be used for ruling out the limit cycle oscillations. So we will complete that section and then we will move on to the tutorial session where we will just see how to plot the different phase portraits and all in our using the equations which we know. So these are just the books and references, and these are the videos, so you can refer to. So so we will begin with the session 7. So previously we saw how to use the gradient systems approach and the Lyapunov functions for ruling out of the closed orbits. Finally, we are left with one more method called the Dulux criteria. So I will explain that here. So in the session, in the last session, in the methods to rule out closed orbits, we discussed the gradient system method, where we said that if you are able to write it as gradient of the function variable, then we can say that, so if you are able to write x dot as a function of gradient of the potential function, then we can say that the system will not have, such systems will not have any closed orbits. Then we looked up into the Lyapunov functions. So in this system we came to know that if you are able to define a Lyapunov function, then we can say that which is a representative of the energy of the system, and if you are able to construct a Lyapunov function such that it is greater than 0 for all x not equal to the x star conditions, and v dot, that is v is greater than 0 for all x not equal to x star, and v dot is less than 0 for all x not equal to x star conditions. If you are able to meet, then we can say that your system has a particular function called Lyapunov, has a variable representing as a Lyapunov function, which can be used to represent the system energy, and this can be used to say that your system is not having any solution, or not solution, it doesn't have any closed orbits. Now the third method which we will learn is called the Dulux criteria. So in a Dulux criteria, what happens is, so this is also a method of ruling out of closed orbits, and it's based on a theorem called Green's theorem. So we might have learned this in mathematics, called the Green's theorem. So what the theorem states is, so the definition, what it states is, say you have a plane, some plane mentioned over here, and let you have x dot is equal to f of x be a continuously differentiable vector field defined in a subset, say on a simply connected, so it's defined on a simply connected subset R of the plane. So say you have a section and you have a simply connected subset R inside this, and if you are having such a subset and if there exists if in this case if there exists a continuously differentiable real valued function. So this is important. If you are having a continuously differentiable real valued function, say we call it as g of x, such that you are able to write it in the form gradient of g of x dot. This has one side throughout the subset R. If you are able to prove this on condition, then we can say that the system follows this Dulux criteria and there are no closed orbits. Closed orbits lying entirely in R. So this how they prove is, so it's similar to what we have discussed in the previous sessions. So the proof to prove this thing is, so they say that initially we will consider that suppose there were a closed orbit so if this is the condition, if there was a closed orbit C lying entirely in the region R. So this is what initially we consider. So we say that as we have done previously, if we are able to prove that we are able to contradict this condition, then we can say that there cannot exist any closed orbits in the system. So what we meant here is, so you have a region R and you have a, say you have a closed region C over here. Then from the Green's theorem, we can say that the surface integral of the gradient of this g of x dot over the area is nothing but line integral of over the curve gx dot times the normal vector along a small length dl. So what this means is like, so here if I abbreviate that, n is nothing but the outward normal and dl is nothing but the element of the arc length. So this is a small element of the arc length which we are considering over the C. So if you consider this, say I am calling this as the left hand and I am calling this as the right hand. So if we consider the left hand, we can say that the region, the double integral over, it must be non-zero, since we are considering the gradient of g of x dot, which needs to have one sign in R. Have one sign throughout R is what our condition was. So that means this value on the left hand side should be a non-zero value. Whereas if you consider the right hand side now, consider the right hand side, and if we say that this c is a trajectory of the system, then the any tangent to the system will give you the x dot velocity, whereas the normal vector n will be perpendicular to this x dot, since you are considering c as a trajectory of the system. If since okay, 1 second, I'll just since c is a trajectory of the system, so the x dot is tangent to this trajectory.
Today after dinner, right? Meeting. Okay, what time?
Trajectory and
okay, how discussion with
the normal vector will be
it was 9 o'clock
perpendicular to the x dot. So now if you look into that, then this g into x dot n, this becomes to a tends to 0, since dot product of n two perpendicular vectors will tend to 0. So this means the left hand side is not equal to the right hand side, and there is a contradiction in the thing. There is a contradiction, and hence this implies that no such C can exist in R. So this tells that, so if you are able to prove that your system has a function like gx dot of this, and it has a single sign throughout the region R, the mentioned R, then you don't have any closed orbit. Closed orbits. So this is the dual-X criteria which we have mentioned. So, and here also the one of the main issues is in the dual-X criteria, the function g of x finding, there is no standard algorithm to find the g of x. Usually some functions like g equal to 1 or equal to 1 by x to the power a y to the power b e to the power ax or e to the power ay. These are the general g functions which usually are mostly applicable to different scenarios which people have tried on. So we will just look into an example of how to use the Dulux criteria. Say you have a system x dot is equal to x into 2 minus x minus y, and you have another system called y dot, which is nothing but y times 4x minus x square minus 3. Now if you are given two systems and we need to check if the system has closed orbits in the first quadrant, so where x and y both are greater than 0. So before this to check, so the reasonable solution which goes is we take g as a function of xy. So if you are taking such a variable, then so the condition which you need to check is del of g dot x dot. So this is nothing but del is nothing but dou by dou x of gx dot plus dou by dou y of gy dot. So if you are taking that condition, so then dou by dou x of g is 1 by xy, and x dot from this given equation you can write it is nothing but x times 2 minus x minus y. At the same time, dou by dou y of 1 by xy times y dot is nothing but y times 4x minus x square minus 3. So if you expand it, you will see that you will remain with dou by dou x of 1 by y 2 minus x minus y plus dou by dou y of 1 by x times 4x minus x square minus 3. Now if you take the derivative of it, you will see that, so this 2 by I times dou by dou x when compared to this will be 0, then you will left out with minus 1 by y plus dou by dou y of 4x constant will be 0, this will be 0, this also x is taken as a constant, 3 is also constant, so this will be 0, so you are left with only minus 1 by y. So this implies for x greater than y greater than 0, your del dot g of x dot is always less than 0 for x greater than y greater than 0. So this implies we have g and f satisfy the required conditions. So according to Dulux criterion, there are no closed orbits in the x comma y comma 0 or first quadrant. Yeah, so this is one example which you can refer to. So we will just look into one more small example. Say you have x dot is equal to y and y dot equal to minus 6 minus y plus x square plus y square if you have. Now if you want to check does this system has any closed orbit, so here the function which we will try to use due to the if you look at it, we have x square plus y square, so we usually prefer exponential function, and you take an arbitrary like e to the power minus 2x. This g function, there is no rule, we need to take arbitrarily and check the equation. Now if you take a equation of this form, you will just do that same procedure. X dot is nothing but dou by dou x of gx dot plus dou by dou y of gy dot. So this is nothing but dou by dou x of g is e to the power minus 2x, x dot is y, plus dou by dou y of e to the power minus 2x times minus x minus I plus x square plus y square. So this finally results in, since y is constant, this is nothing but minus 2 times e to the power minus 2x, plus for y x remains constant, so this term will go to 0, first term, and the second term you will see that you have e to the power minus 2x taken out, plus dou by dou y of y square is nothing but 2y. So now you are left out with minus 2y e to the power minus 2x plus e to the power minus 2x plus 2y. So if you rearrange it, you can write it as minus 2 e to the power minus 2x times y plus, okay, so here one more e to the power minus 2x multiplication will be remaining, so it will be there. You take e to the minus 2x common, then you are left with, okay, so here, 1 second, this should be minus because you had a minus in front of it, so you have minus 1 plus 2y remaining. So this implies when your x, so if you add it up, you will see that you are left out with only minus e to the power minus 2x. So you can just cancel out here itself. Okay, so this means for x greater than 0 or x greater than less than 0 also, we can see that this term always is negative. So this satisfies the Dulux criteria of saying del of g of x dot has a same sign for a given region R. So we can say that there are no closed orbits in the system. So there are no closed orbits exist in the system. So these are the three criterions: gradient system, Dulux criteria, and Lyapunov functions, where you can use them to rule out any closed orbits are present in the system or not. Now we want to look into rules where we want to say establish that closed orbits exist in a particular system. So now we look into the rule to say there exist closed orbits in the particular system. So in order to follow, so there was a following theorem in this direction, and this is a key theoretical result in nonlinear dynamics, because the theorem that we are going to discuss, it implies that chaos cannot occur in the phase plane. It was the theorem that was able to prove that. So it's called the Poincare-Bendixson theorem. So we will discuss what Poincare-Bendixson theorem means. So for that, different conditions were mentioned. So suppose that, so the first condition is R is a, so any region R is a closed bounded subset of a plane it's a closed bounded subset of a plane. So this is like you have a plane and you have a region R which is a closed bounded subset which is closed within that plane, and if you are having such a region R and x dot is equal to f of x is a continuously, one second, I'll just see if recording, yeah. So x dot is equal to f of x is a continuously differentiable vector field on an open set containing R. So it should be a continuously differentiable function such that it can move smoothly inside this region R. And another important condition is R does not contain any fixed points. So now if you are not having any fixed points in the system and your system is a closed bound region R, then there are only two possibilities. Then there are two possibilities in the system can. One is either the trajectory, say you have a trajectory C inside the system, you have a C inside the system that is confined in R, then so if it starts in the region R, then it continues to remain R forever. So if you are having such a trajectory C and it is inside this bounded region R, then either if this trajectory is C, then either C should be a C itself can be a closed orbit. So that means you have a plane and if you have a region R and this curve itself, C itself, it can be a closed orbit. So that is one possibility you can have. Or the trajectory spirals towards a closed orbit. As t tends to infinity. So since we have shown that trajectories will not intersect and within a bounded region the system, if it's repeating, then it should either be a closed, the C should either be a closed orbit, or in this plane where you have the region R, say you have a closed orbit and your trajectory spirals towards this closed orbit. So either any one of these the system will be exhibiting. So both these means that there exists a closed orbit. There exists a closed orbit in the system. So these are the main things for of point. So these are the key assumptions which we take to check if you are able to satisfy all these four conditions. Then we say that your system obeys the Poincare-Bendixson theorem and you can say that your system possesses any, you can say that the system possesses a closed orbit in the system. But proving this, so in a simple way to prove this, so you take a region R as shown here, and since we are saying that there is a closed orbit inside the system, so for the closed orbit, now if you see this within this region, so this is actually your region which we are saying. So this is the R, actually this is the region R which we are saying, and just write it. So this is the region R. Now, so when applying the Poincare-Bendixson theorem, it's easy to satisfy the conditions. So these two conditions, that R is a closed bound subset of a plane, that you can clearly see from this, you can establish them. Then finding a x dot is equal to f of x, so dynamical systems, they usually follow these things, and R does not contain any fixed points. So we can just know how the fixed point is within the system or not by using different methods. Whereas the fourth condition is finding a trajectory C to check whether it exists in the as a closed orbit, or it moves spirally towards, it's spiral towards a fixed point or not. To check that, it's the challenging part, and so a standard trick is to use a trapping region. So this region we call it as a trapping region, the trapping region, and it's a closed connected set such that the vector fields, so this closed trajectory will have a vector fields that are, any vector field if you draw in this system, this should be moving towards the fixed point or the closed orbit here, and anything that tries to move away from this will try to move towards the outer region or to the outer R region. So a closed connected set such that this vector field points inwards everywhere on the boundary of R, then all trajectories in R are confined. So this means that you have only two ways, either you come towards it or you move towards outside and move in a circular path here. So if you are able to, that there are no fixed points in R, and if you are by the third condition we say that there are no fixed points in the system, then we can say that you obey the Poincare-Bendixson theorem, and we can ensure that R contains a closed orbit. So you create a trapping region for your system and find the vector field, how they are going towards or away from this trapping, within this trapping region, and from these vectors you can say that the vector will make your flow go like this towards the system or move out and remain within this bounded region. So eventually it will be going out to it will spiral out towards a fixed closed or itself, the curve which you have selected itself will move towards is a closed orbit. So this is how you say, using Poincare-Bendixson theorem, you explain how you have a closed orbit for your system. So there are different examples in the textbook. So important thing from the Poincare-Bendixson theorem was, the Poincare-Bendixson theorem is one of the central results which says that, so it's an result which says that the dynamical possibilities in the phase plane are very limited, because either it can move towards a fixed spiral towards a fixed point is the only thing it can be done. So it's very limited. If a trajectory is confined in a closed bound region that contains no fixed points, then the trajectory, so it's very limited, since in a closed bounded region closed bounded region that contains no fixed points. No fixed points. The trajectory must eventually approach a closed orbit. So nothing more complicated, or the dynamics you can't observe any other complicated dynamics. It can either go to the closed orbit or spiral towards a closed orbit is the maximum it can do within this bounded region. So this result tells, it depends crucially on the two-dimensionality of the system of the plane. It depends on, and it says that for higher dimension the Poincare-Bendixson theorem will not be applicable, and trajectories, so the trajectories will not be moving as we have explained here. They may wander around forever in a bounded region without settling down to a fixed point or a closed orbit. So in some cases these trajectories, so in a 3D condition, when we are considering the trajectories may wander around the phase plane, and without settling they may be attracted. They may be attracted to a complex geometric object. So it's like you will have a very wide, without the trajectory will never intersect, but your trajectories will wander around and they will be forming very complex geometric object. So these are usually called a strange attractor. So this strange attractor, okay, we will discuss this. It's a fractal set on which motion is aperiodic and sensitive to tiny changes in the initial conditions. Now this sensitivity makes the motion unpredictable in a long run, and this is a characteristic of the chaos which we will discuss soon. So this is a characteristic of chaos where it is very sensitive to initial conditions, and predicting in a long term is not possible because they are very sensitive to these small initial conditions. So the main important takeaway is the Poincare-Bendixson theorem implies that chaos can never happen or occur in the phase plane. So this is one of the important results in nonlinear dynamics. It says that why you don't have any chaos present inside a 2D or a phase plane, why your system will not exhibit any chaotic behavior. So this you can mention the Poincare-Bendixson theorem and you can claim this. So this is one of the important results you need to know. So now there was much of a great deal of research in the nonlinear oscillations during the period of 1920s to 1950s, and a lot of work were carried out using, as I mentioned, in the radio and vacuum technologies were interesting at this 1920s to 1950 regions, and people were modeling that, and it was found that many oscillating circuits could be modeled using a second order differential equation. So it was found that So it was found that the many oscillating circuits could be modeled by a second order differential equation which is of the form x double dot plus f of x into x dot plus g of x equal to 0. So if your equation is in this form, and it is known as Lenard's equation. Now this equation is a generalization of the van der Pol. So if you remember, the van der Pol equation was somewhat like this: nu into x square minus 1 x dot plus x equal to 0. So it's a generalization of this van der Pol equation, and it can be interpreted mathematically as an equation of motion for a unit mass subjected to a nonlinear damping force. So if you shift this to this side, it's nothing but minus f of x into x dot minus g of x. So this term refers to a nonlinear damping force, and this term refers to a nonlinear restoring force. So it's like in a spring mass system, these are the damping force and this is the restoring force in the system. So if you had pulled it, this restoring force taken by the spring can be taken as this minus g of x, and minus f of x is the damping which reduces these oscillations. So from our standard method, where we used to reduce the second order equation into two first order equations, what we do is we take, say, x dot equal to y we take, then substituting this into this equation A, we will get y dot, that is x double dot is nothing but minus f of x times y minus g of x. So these are the two first order equations which we have, and it is proved that this system has a, for this particular two equations, you will have a unique stable limit cycle under appropriate f and g equations. So why we are studying this is, so Lenard's equation, if you are able to prove that your system follows this Lenard's equation, and if you are able to build one function f and g, then we can say that your system possesses a unique stable limit cycle in this, for that. So in order to show that, so the Lenard's theorem states this. We will not go into the derivation, but we will just see what the Lenard's theorem is and how we can use it for confirming that there are closed orbits present in the system. So what Lenard's theorem states is, suppose that there is a function f of x and g of x which satisfy the following condition. So the conditions are, first one is f of x and g of x are continuously differentiable. So if they are continuously differentiable over x, for all x, and the second condition is the function g of minus x should be equal to minus g of x, which is nothing but for all of x, that is g is an odd function, g should be an odd function, and the third condition is this g of x should be greater than 0 for all x greater than 0, and fourth condition is the function f of minus x should be equal to f of x for all x that is f is a even function. So f should be an even function, g should be an odd function, and both f of x and g of x should be a continuously differentiable, and g of x should be greater than 0 for x greater than 0. And the fifth condition which needs to be satisfied is that there exists a odd function capital F of x such that the integral 0 to x, the small f of x du has exactly one positive 0, or it should be confirmed that it will not have any negative values in that. It should have a one positive 0 at x equal to some value a, and is negative for 0 less than x less than a condition, and it is positive and non-decreasing for x greater than a. So these three conditions should be met by the, if it is met by this system, x greater than a, and so this capital F of x tends to infinity as x tends to infinity, so that you can directly correlate. So then the system will have, then it is said that then the system has a unique stable limit cycle surrounding the origin in the phase plane. So this is, you can conclude that it's obvious that your function is an odd, f of x and g of x is an odd function, and in a simple oscillator we saw that if your system oscillates, then it oscillates around this as in circles. So this is result is easily interpretable, and the assumptions on g of x, that is g of x minus g of minus x tends to minus g of x, it's nothing but the restoring force acting like an ordinary spring. It's just like it's pulling back, and it tends to reduce any displacement, whereas the assumption on the f of x, where f of minus x should be equal to f of x, imply that the damping is negative at small values of x and positive for large values of x. So since the small oscillations they pump up and large oscillations are damped down, the system eventually tends to settle into a self-sustained oscillations of some intermediate amplitude. That's how you end up into these kind of circles in the phase plane, which is a representative of closed orbits present in the system. So once, if you are able to find these 5 measures are agreeing, and then we can say that our system will have a unique stable limit cycle present in the system. So we will do one example here. So the example, we will take the van der Pol equation, which is nothing but x double dot plus mu into x square minus 1 x dot plus x equal to 0. Now for this, if you observe, the f of x is nothing but mu into x square minus 1, whereas g of x is nothing but x. So for the 1 to 4 conditions, if you observe, you can see that f of minus x is nothing but mu times x square minus 1, which is nothing but f of x. At the same time, g of minus x is nothing but minus x, which is nothing but minus g of x. So both the conditions are met, and the third condition, g of x should be greater than 0 for all x greater than 0, and that is true here. So we are, and f of x and g of x both are differentiable. So we have seen 1 to 4 conditions all are met now. Now for the fifth condition, for the f of x, so say fifth condition to it, so it's like you have 0 to x, f of u d of u should be, it should follow certain rules. So in this case, if you are taking 0 to x, f of u is nothing but nu into x square minus 1 dx. So here x it is instead of u. So if you solve it, you will get that u into x cube by 3 minus x minus x. Now our first condition was when x is equal to some value of a, your system, this capital F of x should be having a value equal to 0, positive 0 it should have. So if you take a as, say, this is nothing but nu times x, x square by 3 minus x. Okay, if you take the 3 out also, you will just multiply, that will be equal to x square minus x. You will be remained with, sorry, 1 second, I'll just rewrite that. So if you take the 3 out, then you are left with x cube minus 3x, and further you reduce by taking it with x out, so you will get x square minus 3 remain. Now if you take a equal to root 3, then you can see that your f of x is equal to 0, because x square is there, root 3 square is 3 minus 3, which is nothing but 0. And for the second condition, just continue there, that may be left somewhere there. So for the second condition, where the f of x is, say this was our equation, and the second condition we were looking at, and the second condition was between 0 less than x less than a, your f of x should be having a negative value. So if you check here, if a is root 3, then your f of x is nothing but nu times x by 3 into, so less than 0 less than a, root 3. So if it is less than root 3, so this root 3 square will be a lesser value than this. Eventually this will be a negative value. So f of x will be a negative value. So it satisfies the second condition. And if you check the third condition, where for x greater than a, so that is x greater than root 3, if it is, your f of x value is nothing but nu times x by 3. So if it is greater than that, so 3 square root 3 is nothing but 1.7. So 1.7 more than that. So if you take 2 square, it's nothing but 4 minus 3. So it's actually positive. So it's a non-decreasing value for x greater than root 3. So you were able to show that the fifth condition is also met in the Leonard's equation. Leonard's equation is met. So we can say that the van der Pol has a unique stable limit cycle. So this is one equation and theorem that tells that you can have a limit cycle present for your system. And so in connection to this, there is a small topic, we will not discuss much on this. It's called the weakly nonlinear oscillator. Weakly nonlinear oscillators. Here what they mention is, so here we looked at x double dot plus f of x into x dot plus g of x equal to 0. Instead, if you only had x double dot plus x equal to 0, this is a equation of a simple linear oscillator. Whereas if you are having a small perturbation of the size epsilon, a small perturbation if you are having in this system, then your system will behave like x double dot plus x times you have some epsilon times a function of h and x dot equal to 0. So this will be your system of equations. So this kind of very small, but since it's a very small perturbation, this equation is usually referred as weakly nonlinear oscillator. And so there are two basic examples of this. One is the van der Pol equation, which is nothing but x double dot plus x times epsilon times x square minus 1 x dot equal to 0 in the small nonlinearity. So in the limit of small nonlinearity, we say that we can write x double dot plus x times x square. There is one more equation, x cube equals 0, and this is one example, and this is under the limit of low nonlinearities. And there is one more equation called Duffing equation, where x double dot plus x plus epsilon times x cube equals 0 is the equation for that. So these are two broad examples of weakly nonlinear oscillators. So to illustrate this kind of phenomena, we will just look into the phase plane portrait of this system. I'll just show you the phase portrait for this. So you can observe that. So here the first equation which we have written, x dot equal to y and y dot equal to minus x, and the epsilon value I have given here is 0.1 for small nonlinearity times x square minus 1 into y. So this is the van der Pol equation which we have considered. And for such small nonlinearities where the initial conditions are close to the origin values, you will observe that if you generate, you can observe that the trajectories is a slowly winding spiral, and it takes many cycles of amplitude. So you can observe that it takes many cycles of amplitude for the amplitude to grow substantially. So here for this to grow substantially, it takes many oscillations because of this small nonlinearity present in the system. It takes many oscillations and then it spreads out to high amplitude oscillations. You can observe from here. Then it moves out to very high amplitude. So it asymptotically grows to very high amplitude oscillations. Then, so this is one of the weakly nonlinear oscillators which we just barely mentioned it. And one of the other topics which we will just touch upon is called the relaxation oscillations. So if you observe the question for a given particular two-dimensional system, does it have any periodic solution, is what we were addressing till now. And now if we ask in a quantitative way that given that you have a closed orbit exist, what can we say about the shape and period of this orbit, or that how this with time how this evolves in x. So this problem can't be solved exactly, but there are a lot of approximations in some parameters if you are taking the extreme conditions like large and small oscillations. If you are considering, say for Van der Pol oscillator itself, we have the equation of the form x double dot plus nu into x square minus 1 x dot plus x equal to 0. So this is the equation you had, and for very high nonlinearity where nu is very greater than 1, which is the strongly nonlinear limit, I'll just share the screen once. So as I mentioned that, so the Van der Pol oscillator, it has the form x double dot plus nu into x square minus 1 x dot plus x equal 0. For the case where nu is very greater than 1, it is the strongly nonlinear limit is what the region we are considering. In these cases, we see that the limit cycle consists of an extremely slow build-up by a sudden. So it's like you have a slow build-up and there is a sudden rapid discharge of the energy present in the system, and these kind of oscillations are usually, so these kind of slow build-up and rapid discharge is usually what referred to as relaxation oscillations. Relaxation oscillations, because the stress accumulated during the slow build-up, that is this region, is released at a very fast during the sudden discharge is being made in the next during this discharge process. So these kind of relaxation oscillations are observed in many scientific different ways. So I will just show you one of the relaxed oscillation that we call as stick slip oscillations. In this stick slip oscillations, you will observe that there is a smooth slow build up and there is a rapid coming back of the system here. So I will show you how the stick slip oscillations are seen. Let me share the screen once again. Yeah, so if you look into this, so this is a stick slip motion for a mass on a moving belt is what's shown here. So if you see here, so you can observe that there is the initially blue colored region. When it is there, it's moving forward with a, so they are showing a slow motion of it, where you can see that while in the forward path it is stick and it's moving very slowly in the forward, but the reverse path it comes back at a very fast rate. Similarly, you can observe that it goes very smoothly in the forward, and once it reaches a particular point, it is there and it comes back, discharges at very fast rate back. So this is what a simple example of a stick slip oscillations, and so they are explaining it in further with stick slip conditions at a very fast rate. So yeah, so this is an example of a relaxation oscillation where you have a slow build up and a fast discharge. So in the current, so we have learned what is the Poincare-Bendixson theorem, we have seen the Lennard systems, we have looked up on the weakly nonlinear oscillators, and we have seen what are relaxation oscillations, and this is the diagram which I mentioned. So there is a slow build up and there is a fast discharge present in the system. Now we will just I will just go through in the tutorial one. Okay, I was expecting some. Okay, you can watch this video, and if any comments are there, you can ask me further. So in this tutorial one, we were supposed to see how the different diagrams, the phase portrait and all this were being plotted in the given system. So for that, solving the equations on computer, how different we saw different phase portraits and vector fields being shown in the diagram. In the phase plane portrait, if you see, we are able to show this kind of vector diagram for this. Then how can we create this using the MATLAB is what we will try to look into. So for that, so we will just start with basic numerical integrations, because nonlinear dynamics you need to know the numerical integration parts to plot the different dynamical set of equations. So for that, so the initial basic method which you need to know is called the Euler's method. So we will just discuss the theory first, then we will go to the code. We'll just discuss the theory, and then so you can try out this. I will share the codes to you. You can try out these codes, and we will, if any doubts, you can solve it in the next class. So so you need to be aware of some of the numerical integration methods. So in which first we will deal with a basic method called the Euler's method. So in the Euler's method, so we have a differential equation x dot is equal to f of x, and which is subjected to initial condition, which is subjected to the initial condition of x equal to x naught and t equal to t naught. If you are having this condition, so we need to find in a systematic way to approximate the solution for, so we need to find the solution for x of t and see how the system evolves. So for that, suppose, so you know, to understand this, what actually the Euler's method do, say that the way we have a fluid, say you have a fluid, it's a fluid, it is flowing steadily along the x-axis direction. If it is, say we are considering there is a fluid which is flowing along the x-axis direction with a velocity f of x, and so it has a velocity of f of x at the location x, which is shown here. So now imagine that along this phase, so now if you imagine that this is carried along this phase plane, this image fluid particle is moving along this phase plane, and initially say we were at a point x naught, and the local velocity of that is f of x naught we consider. Now if we take a short window of say delta t, by that time the particle has reached to this point where it has, so we know that velocity is nothing but distance by time. So that means the within this short time the distance covered is nothing but the velocity into time it has taken. So that is, the distance covered is within this delta t time is nothing but the velocity f of x times the delta t. If you are considering the initial point, then it is f of x naught times the delta t. Now okay, you may think that within this small delta t the velocity may be decreasing, but we consider that the delta t which we are considering is sufficiently small such that if there is very little bit change within this small delta t, the velocity nearly remains constant throughout this thing. And if you are considering a sufficiently small delta t, then this assumption remains preferably good only. It's reasonably good to, for a very small delta t, you can consider the velocity which remains approximately same. Then for the next instant t naught plus delta t, your distance traveled by the system is nothing but x naught plus f of x naught times the time delta t. So this is the new approximation, so we will take this as x1. So x1 is nothing but x naught plus f of x naught times delta t. Now if we iterate, our approximation has taken to it. Now if you do the same process over the next point, so this was your x1 say. Now if you take one more delta t and you take the particle here, now say this is your x2. So for the given x2, you can say that it is nothing but x1 times f of x1 times delta t. And if you forward it to different points, this is nothing but xn plus 1 is equal to xn plus f of xn times delta t. So this is the simplest method called the Euler's method, where as you march forward for a very small delta t time, you can find the solutions of x of t for each of the points. Now if we try to visualize this in a, so we will try to use this in a code and see how this behaves. I will share the screen once again. Yeah, so I will just show you in MATLAB. I hope for the previous session with Shruti you were installing the MATLAB. Now, so initially for an, say I just want to plot the equation of the form y equal to x square. Okay, so the equation which we take here is x dot is equal to x square is the equation which I have shown here. X dot is equal to x square is what we take here, and okay, I will just write it down so that it will be helpful. So here if we consider x dot is equal to x square is an equation which we are considering. So if you do, this can be normal integration you can do, where you can find the analytical equation. This is nothing but dx by x square is equal to dt. So if you integrate it, you will get x to the power minus integral x to the minus 2 dx equal to integral dt. This is nothing but x to the power minus 2 plus 1 by minus 2 plus 1 is equal to t plus integration constant c. So this means t is equal to, so okay, now if you have given an initial condition, you can find the value of c. So t is nothing but x to the power minus 1 by minus 1 minus c. So this is nothing but minus 1 by x minus c. Now so we take initial condition, say c is equal to 10 if you consider. Then you can find the value of t for a given condition. So our interest is to find the velocity and get the, so we need to plot this actual plot here. So we need to plot x versus, so this is your time and this is the value of x which you need to plot. So for a given initial condition, you can get the different values of that. So I will just plot for a given value. So 1 second. So here, so this is a critical condition over here. So minus 1 minus 10 by x. So if you write x 10x by x is equal to t. So if you write it in terms of x, this is nothing but minus 1 minus 10x over t. This is nothing but minus 1 by t minus 10x over t. So if you take x common, then it is 1 plus 10 by t times x is equal to minus 1 by t. Okay, sorry, 10 by t. So x is nothing but minus 1 by t times 1 by 1 plus 10 by t. So it is minus 1 by t times t by t plus 10. So if your t is equal to either 0 or t is equal to minus 10, your system will blow out, because you 1 by 0 it goes out and x will not have very high values. So you take a initial condition such that if it is values are less than, so we take conditions from x is from 1 to 9 is what the initial conditions which we take. So for up to t equal to 1 to 9, how your system behave, we will just plot it in the MATLAB, and we will try to use the Euler's method to plot that graph once again. Yeah, so this is what we were discussing. So initially I gave an empty arrays to store the values, then I am changing the values of x from 1 to 9 such that I am finding the values of y. So initially I took t value as x values will change from 1 to 9, so y, that is v dot value, changes by 1 by 10 minus x. So we took the value of 10 here. So you can just now save these values. So these steps are to just save the values of y what is getting for a given x. Now if you try to plot it, we'll just plot them, and you will see that this is nothing but a parabola. Y equal to x square is nothing but a parabola. So you are getting a near parabola like thing for this different points from 1 to 9. This is the actual plot which we have got. Now if we try to use the Euler's method to plot this graph, so initially you need to give a initial condition and you need to give a small delta t change, what you are you need to small delta t for which you are considering the Euler's method. Then now you are changing the x values from 1 to 9, and you know that n plus 1 is nothing but xn, that is x of the I value, plus dt times the x square. Since your function here is x square, so we are taking xx of I the whole square, and so we are plotting it for a time from 1 to 9. So if we are plotting it on this plot, we will see that so the Euler's method, so this orange color is the Euler's method, and this is the actual plot which we have plotted using the analytical method, and we see that there is a slight difference. So the numerical error builds up as since your approximations are delta t is very small, you consider it is very small, so this system diverges out after certain small values, it diverges out to very high, diverges out, or the error between them increases. So that's the shortcoming of Euler's method. So in order to improve that, what they did was, it's called a, so we just write it down. So in order to improve that, over that, there is a method called modified Euler's method. So you can take any analytical equation and you can try this out for a simple equation, and you can do the remaining steps. So for this modified Euler's method, what they do is, so as done by in the Euler's method, you will find the x n plus 1 is equal to xn times plus f of x naught xn times delta t. So they take this one trial step, they say here. So they find initially this trial step, and now the actual value of xn plus 1, which is the actual step to get the required solution, is considered as xn plus the average of the velocity for xn plus the velocity for the xn plus 1 tilde times delta t. So what they did was, they took the average of the velocities that came from the normal Euler method, that is this xn plus 1 tilde, and they took the average of the original value f of xn. So with total f of xn plus f of xn plus 1 tilde by 2 is an average of the velocities. With that average velocity is what the system is, the particle moving, is what the assumption comes here. And if you use this modified Euler's method into your system, how they found that the system shows a higher accuracy in finding and close behavior to actual system dynamics. So we will see for the condition which we are considering here, will that be useful. I'll just share the screen with the MATLAB. Yeah. So now in a modified Euler's method, as previously, you will mention the initial conditions and delta t, and for now in the initial point you need to find the initial values. So xxi plus 1 will be xi plus delta t times xi square. This is the normal Euler method. Now the actual xxi plus 1 should be the xxi plus half of the mean of the velocity xx. So f of x is nothing but x square. So xxi square plus the new xxi plus 1, which is updated here, that will be taken here, and squaring of that will be done, and you take a mean of this totally and you multiply with the delta t, and then you sum it over the different values of x. And if you use that and if you plot it here, you will see how that system behaves here. So now so this is what the modified Euler's, sorry, we have this thing is wrong. Okay, so this is the actual, this is the Euler's method, and this is the modified Euler's method, which is plotted here. So you can observe that the modified Euler's method is much better than the Euler's method. It is giving a good accurate way of more close behavior and how the system is behaving. Now here also it's improved version of Euler's method, but there are higher orders where you use third and fourth and fifth higher orders for this, and then you take the average of that. So a well established thing is what you call Runge-Gutta method. So we will just look into what is Runge-Gutta method, and then we will look into the code. So you can use higher order terms in this, higher order terms of third, fifth and all you can use, and you can get more accurate things. So instead of that, there is one method called the Runge-Gutta. So here we will study Runge-Gutta fourth order method. So in the Runge-Gutta fourth order method, so I will explain how this works. So we need to find 4 parameters. So they are called K1, K2, K3 and K4. So you need to find all these 4 parameters, and so they define these parameters. So we are considering the equation x dot is equal to f of x, and for finding K1 it is nothing but f of xn times the delta t, and K2 is nothing but f of xn plus K1 by 2 times delta t, and K3 it is defined as f of xn plus K2 by 2 times delta t. So here K1 normal function, K2 you take a half of the K1 and then add it up and then take the average, and K3 you take xn plus K2 by 2 times delta t, and K4 you take xn plus K3 times delta t. So once you found the 4 variables K1, K2, K3 and K4, when these parameters you have found, the final solution xn plus 1 will be xn plus 1 by 6th of the K1 plus 2K2 plus 2K3 plus K4. So you will, so this is the final equation that you will have to get the next value of solution of x of t in the next point. So once you get this, so now, so in either you use any Runge-Kutta, so we'll just first see how this Runge-Kutta works, and we will see what is the problem with numerical integrations and how much accuracy you can get over. So we saw the actual and the modified Euler and Euler method we saw. Now in a Runge-Kutta 4th order method, as I shown, for a given initial condition at delta t, for Runge-Kutta you generally need not take very low delta t's. That's the advantage of using a Runge-Kutta. So you will find the K1 value, that is delta t times the xx of I of square, and you take K2 which is x of I plus half of K1 times the square of it, and K3 is dt times x of I plus 0.5 K2 of square of that. So f of x is nothing but xi square, but xi is nothing but xi plus 0.5 times K1 when you are finding K2, and when you are finding K3 it is x of I plus 0.5 times K2, and here K4 is nothing but x of I plus K3 and square of it. So the final solution, that is xn plus 1, will be xn plus 1 by 6th of K1 plus 2K2 plus 2K3 plus K4. So, and you can put it into a for loop, and you can get the different, for a given different values of t, you can get different values of x in the next steps. And if you plot that, yeah, so you can see that, one second, this is at the end we have plotted, so this is not properly coming. So yeah, so this green is the Runge-Kutta method, and you can see that it's better than the Euler's modified Euler's method, and there is a steep error when this is occurring. This is because we have taken very low number of values for these conditions. If you take very minor steps for many very low, so we have taken delta of t of 1. So if you take very low values of delta t, you can iterate it and you will get very close by near values for the actual curve, for the shown actual curve. So this is the numerical method of finding the values of solutions of a given dynamical system, and using these Runge-Kutta methods we can solve different dynamical systems and solve different equations. You can numerically integrate that, and you can use these methods. Most preferably people use this Runge-Kutta 4th order method, where, and if you are having a noise and all in the system, then you should be using stochastic Runge-Kutta method, where you will be using different noise intensities into the system. So we will deal with without noise. We will be deterministic system we will be considering, and so this Runge-Kutta method will be enough for this case. Now, so as I have shown here in the phase plane portraits, we were seeing that there is, you can see the vector plot which were shown here in the plots. Now how to create these kind of vector plots when you are given a dynamical system equation? So for that, for plotting that vector field, so initially you need to mention the size of the mesh or the screen x comma y plot. What is the x and x-axis values and y-axis range you need to mention here. So for an example, I have mentioned here -2 to 3 I have mentioned, and -1 to 2 is the y-axis range. So now I have fixed a, so it's like a graph sheet you have fixed with certain x-axis limits and y-axis limits you have fixed. Now for plotting the vector field, you need to know the slope at each of these points. So we have taken a function f of x is equal, x dot is equal to 1 minus xy square. So we have taken the equation x 1 minus xy square is the equation which we have considered here, and if you take that, we need to find the slope. So slope is nothing but dx by dt, or here if you are having one x and y, dx by dy is the slope. So slope is nothing but the f of x, that is 1 minus xy square. Since you are having arrays of the thing, you should be putting dot here in the system in MATLAB, so that you will multiply each element with the corresponding element and then you square it. So this is the slope value you are getting. Now there is a function called cuber in MATLAB, and for that, if you supply the x and y values which you are finding, and this ones of size, this will keep the size of all the vectors of same size it will be keeping, and s is the slope corresponding to, for a given x and y values, the slope is with the size of 1 is plotted for this. If you are running this particular code, you will see the slope value for a given slope at a given x and y values. The system will plot the slopes of the system. So if you plot that, you will see the vector field. Just close that. So you can see the vectors being plotted here. I'll just, for convenience, I'll just zoom in the scaling factor to 1, and so marker size you can increase further, okay, since you don't have so you can see the vectors, vector field of each so you can see the vectors being going, projecting in the path of which you actual the system x dot is equal to 1 minus xy square equation is going. So you can see how the vector field evolves like this. So the QR plot can give you this vector field. So for that you need, as I shown, you should need to mention the mesh grid first, and then you need to plot the QR plot for this, where you are mentioning the slope for each point, corresponding to each point you are mentioning the slope. Now once, since here all the x and y's are not normalized, so in order to normalize that, we take the length at each of the points. So you have x t comma s is the function now. So you take the mean or the norm of that, that is square root of 1 plus s square. If you take that, you will get a length or a scalar value of called the length. If you divide that length with these slope values, now you will be normalizing it, and you will see that the length of each of them are according to the so the lengths are adjusted according to that, and you can clearly, the system automatically adjusts to the correct flow which we have mentioned. If you look into the previous plot, it was this, just this one, whereas if you now look at this thing, the system is more organized. You can clearly see how the vector field evolves for this given direction. So that's an additional thing. So if you divide this with the length of the slope, you will be able to plot the vector fields corresponding to the required length according to their magnitude. So their magnitudes will never be changing, only the sizes will be changing according to the normalization which we have done here. And so that's how you will be plotting the vector fields as you have seen here. Similar to this, you can plot the vector fields using this QR plot. And so now once you have got the QR plot to plot these things, now if you want to plot a given line over this QR plot, say when we click here, we are able to see a particular line that is moving from one point to another. So how they introduced this into the code is, so for plotting a line, so this is normal QR plot which you have. Upon that they mention, so sim refers to symbols in MATLAB, so we refer symbols x and y for the equation, and then you find the differential derivative of it, that is dx is equal to, say we take here x into 1 minus x is the derivative which we take here. And if you consider this equation, so we consider x1 is equal to solution of the derivative, that is dE, times the initial condition for that, x0 is equal to 1.8 I consider here, and the y variable is what for which it will be solving of. Similarly, the expand option will give you the solution of this x1 and it will plot here. So for this function fxn, what we have mentioned here, for this x1 values, the scalar values which we have obtained from this, we plot the function for that. So for each given condition, from this f of x will give you the values of each plot ranging from 0 to 10 we have mentioned here. So if you use this function fplot, then we will see that, so you can see the, so here I have just plotted x into 1 minus x on this direction vector field. You can change here, so here I have not used the equation 1 minus xy square, instead I am using our normal equation x dot is equal to x into 1 minus x is the equation which I am considering, and I have plotted the QR plot for that. And if you plot only that, you will observe the plots like this. So your vector is moving like this, you can observe it's coming like this and it's moving towards the through x-axis. Now when you want to plot a line for this given thing, so now for a given initial condition x0 is equal to 1.8, you can see how the vector evolves. So this is the line which, when you are clicking at this face plane plotter, when you are clicking at any point, this is the line that is evolving into the system. So you can use this method to plot these values in the QR plot. Now once you have plotted the QR plot you have used, and you have plotted a given trajectory of the system, and your vector fields are emerging towards the x-axis, and you are able to come to know. Now the next step will be to plotting the phase portrait using phase portrait. So there is a special function in MATLAB called the p-plot. So you can use this p-plot phase plot package. So you can either use this method to plot it, or you can directly use a phase plane plot. So here it's a function of time and x, it should be, so it's like dx by dt it should be. So there are two first order equations. So x1 dot is equal to x2 is mentioned here, first equation, and the second equation is x2 dot is equal to minus x1 minus x2. So this is the equation. If you plot this in phase plot, you will see that, so default p-plot will take some 4 or 6 points and it will plot the trajectories for the 6 points. And for this given system, you can see that there is a node and all spiral towards this particular node. So it's like a spirally they are coming towards this stable node. So you can see, these can be changed according to the number of requirements of the points you have. Now if you look into the equation of, so we have discussed this back in the last 1 hour. We discussed about a function van der Pol equation, that is x dot is equal to x2 and x2 dot is minus x1 plus half times 1 minus x square into y. So this is nothing but the van der Pol equation, where you have 1 minus x square times y half into 1 minus x square, and this is for under the low non-linearity conditions. You can see that you are taking 0.5. So in these conditions, now if you, so defaultly this function will take the number of lines to be considered as 4. You can change it by using the function called xplot number, and you can change this number to any number of points you want to plot on this space. So here whenever we are clicking, actually the system is plotting different lines, and you can plot different number of lines here. So that can be adjusted based on these values here. And for this QR plot, if you observe here, if you plot that here, so now this is for, as you know, the van der Pol oscillator will have a stable limit cycle oscillation, as we have seen here. So this is how it is. And for different initial, so here we have given 4, so it takes 4 conditions here, 4 conditions over here to plot the values, and it plots the trajectory of the system, how the system evolves. So this is how the phase plane you can plot for a given system. So you can try this phase plane, phase portrait plotting in your, for different equations which you know, and you can get these phase portraits. And so this kind of phase plane, you can check how this system evolves and how its trajectories evolve as time moves. You can check those equations, and whatever we have learned till now, the van der Pol equation and all, you can use this ordinary function and you can plot the phase portrait for them. So this is the simple tutorial where you can use. So here we have seen that from a small Euler's method of from a direct analytical solution you can plot, and you can use the Euler's method to get the different values, or you can get the modified Euler's method, and most preferably is the Runge-Kutta 4th order method, which is more precise and more accurate, and you need very small delta t for solution. With this method you can get more accurate nearby x-axis values. And if you want to plot the vector fields for each of them, you can use this QR plot, is what usually we use for plotting the vector fields. For plotting the vector field, important thing is you need to know the slope at each point. So the slope is not known by the, so we write x dot is equal to f of x. So x dot is actually the slope of the system, dx by dt. So slope is nothing but the f of x function which you are giving. So here they have considered 1 minus xy square, and you have plotted the mesh grid and vector fields, and in order to make it proper you divide it by the norm of it. Since it's a function of x and s, the slope and the t function, so you will take the norm of that, that is square root of 1 plus s square, and you divide it by this ones and the slope with the particular length. So this 0.5 corresponds to the thickness of the arrows and all, and so you will finally end up into a more standard vector field. And finally, if you want to plot a line over these vector fields to see how the trajectories evolve, you can give a initial condition and solve this particular equation. Take desolve and expand equation function here in the MATLAB to plot these values, and you can plot for a given initial condition how the trajectory evolves. You can explain it using a curve that we have seen. And finally, the phase portraits for the given two equations can be plotted using the pplot function. And so you can check this for different nonlinear oscillator models which we have discussed, van der Pol equation and weakly nonlinear system. Since we have just discussed the weakly nonlinear oscillation for a van der Pol equation, so you can check for a very low values of van der Pol at 0.1. if you are giving 0.1 values, how your system evolves. So you can see that, as we have mentioned, your system takes more number of revolutions near the origin, and then finally it emerges out to, and it exponentially grows to very large amplitude oscillations. So we can see how the van der Pol equation for a weakly nonlinear oscillator for these things, and for a relaxation oscillation which we have mentioned, where the values are extremely large, very greater than 1. So we take 4. If you take, in the case of relaxation oscillations, the van der Pol equation goes, as you can see here, it takes very large time for it to move towards this, and it zips through this loop and it comes there. So it takes very fastly, it moves out through this, and it takes large time for it to move towards this region. So this is how you try to plot the vector fields and the trajectory in the vector fields, and evaluate the phase portrait of a system. So in this tutorial one, you can try these things with different equations which we have studied till now. And so we discussed the Euler's method, and we have discussed the modified Euler's and Runge-Gupta method. So there, as I mentioned, the relaxation, you can plot the x and t values of that, and you will get a curves that are going like this. So you can try out these different methods or different equations. You can try to solve different nonlinear equations mentioned in the system. So I'll just write it down. You can try this, and if any questions are there, we can address it in the next class. So you can try out this MATLAB. So we will share the MATLAB codes here. So in tutorial 1, we have seen the different methods of numerical integration, and saw how to plot the vector fields and phase portrait. So you can check these codes and use it for different equations, and try to plot the phase portrait. Phase portraits. So if any doubts or anything, we can clear it off in the next session. So you can check, I will put it in the same link where we are keeping the notes and all. There I will put up this MATLAB code also. You can try to run these codes by your own and see how you can replicate the results using. So you can compare your results with the p-plane plotters and see how your system behaves, and you can confirm whether your codes are running correct or not, and you can check the different values. So in session 7, we have completed the numerical methods and numerical integrations, and Runge-Gupta fourth order method we have seen, and numerical methods we have seen. So we will now just move on in the next lecture to the chaos theory, and before that I will just discuss some of the 2D bifurcations which we need to know to understand some of the real world problems which we will discuss in future classes. So once that 2D related problems from bifurcations which we need to know. Once we discuss that, we will enter into the chaos, what is chaos and all, and we will further move towards the different topic of strange attractors and fractals and all. Yeah, so that's what I have planned for this session today. You can check out this video, and yeah, I hope if you have any questions we can discuss it. So I will just global bifurcations. We will discuss some of the real world applications also here. So till now in this session, the important thing which we learned was the Poincare-Bendixson theorem and Lennard systems. So Poincare-Bendixson theorem is very important result which was established in nonlinear dynamics for studying this, that chaos is not possible in a two-phase plane, and it was pretty famous at that time. And so then from there on people were interested more onto chaos and how you can model the chaos and all. People started, and how in different systems the chaos is observed in different ways. So we will discuss those things in the upcoming lectures. Yeah, so I think I'll just stop for today. If you have any questions, you can clear it off in the next session, or we can have a session for this session doubt clearing also if you required. Yeah, so this, you can use different equations instead of using x dot equal to x square. You can take different values and try to plot the analytical solution for that and compare the different numerical integration values. So I hope these sessions are useful for you. So if no more questions, we will stop for today. Okay, so thank you very much.